In this video, we're looking at two blocks that are in contact with each other on a level, smooth surface, meaning we don't have to think about friction. And we have an unknown force applied to this pair of blocks, but we do know the acceleration of the blocks. And in part A, we're asked to compute the magnitude of that unknown force, F. And the simplest way to get this done is to just look at the masses as a combined system. So the total mass is 14.5 kilograms. And that one force, the one we're looking for, causes that total mass to accelerate at 3 meters per second squared. Well, if we know the total mass and we know the acceleration, we can find the force that mass is feeling using Newton's second law, F equals ma. There's only one force, so F net is really just that one force. So I have that the force is 14.5 kilograms times 3 meters per second squared. When I run the numbers on this, I get 43.5 newtons. In part B, we're asked to compute the magnitude of the force exerted on the 5 kilogram block by the 9.5 kilogram block. So we're getting into some concepts about interaction forces here. So to get into the details of the interaction, I know that the 9.5 kilogram block feels a force from the left exerted by the 5 kilogram block. Otherwise, it wouldn't be accelerating to the right. And we're going to call that F on the 9.5 due to the 5 kilogram block. So an F with a subscript of 9.5/5. But we also know that when two objects exert forces on each other, they have to obey Newton's third law, which means that 9.5 kilogram block is pushing back to the left on the 5 kilogram block. And the magnitude of that force must be exactly the same and the direction is opposite. And we'll call that the force on the 5 kilogram block exerted by the 9.5 kilogram block. So that's an F with a subscript of 5/9.5. Again, we know by Newton's third law that those two forces are equal in magnitude but opposite in direction. What we're asked for in part B is the magnitude of the force exerted on the 5 by the 9.5. So it's the one on the left here. But the easiest one to access is the one on the right. I can quickly compute the force felt by the 9.5 kilogram block just by looking at its mass and how fast it's accelerating. So the force felt by the 9.5, exerted by the 5. Newton's second law, so F equals ma. The mass is 9.5 kilograms. The acceleration is 3 meters per second squared. And this magnitude turns out to be 28.5 newtons. If we wanted to think about the vector value of this, that's 28.5 newtons to the right. And then we apply Newton's third law and we say, well, the force on the 5 kilogram block due to the 9.5 kilogram block must have exactly the same magnitude. And again, we weren't asked for it, but if we think about what's going on vectorially, that force points to the left. Okay, so we've answered the question, but there's a nice way of checking our work. What we can do is then analyze the net force on the 5 kilogram block and verify that it comes out with an acceleration of 3 meters per second squared. That 5 kilogram block has two forces pushing on it. It has the applied force of 43.5 newtons coming from the left, and it has that reaction force, the 9.5 kilogram block pushing on it from the right. So using rightward as our positive direction here, the net force is 43.5 newtons to the right minus a 28.5 Newton force. That's to the left. And then our mass is 5 kilograms. And what we're trying to do here is solve for A and just verify it gives us the right number. So I do the subtraction on the left, and then I divide by 5 kilograms. And the acceleration does come out to 3 meters per second squared. And now we're confident our answer was correct. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.